Welcome to the video on arithmetic sequences and series. We'll start off by talking about what a sequence is and what a series is. So a sequence is a list of numbers. So here are two examples where there's lists of numbers that go on forever. A series is a sum of a sequence of numbers. So these are two examples of different series. What's unique about an arithmetic sequence is that it has a common sum or difference. So in this first sequence right here, it's pretty easy to see that 4 is being added to each number to get the next number. And in the second one, you can see that 4 is being subtracted from each of the numbers to get the next number. This third one here is a little bit more difficult to find the common sum or difference. So what you can do is you take the second number and subtract the first number. So if we put a common denominator, we get 3 over 3 minus 1 over 3, and you have a common difference of 2 over 3. And you can always check that too by doing 1/3 plus 2/3, which equals 1, so that gives us our second number. And we can test it with our second one. 1 plus 2/3 is 3 over 3 plus 2 over 3, which equals 5 over 3, which is our third term here. So that's how we know that the sequence is continuing with the difference of positive 2/3. The first important formula that you need to know for arithmetic sequences is the recursive formula. So with this formula, you can find any term if you know the term before it and your common difference. So here is an example. We have 5/2, 2, 3/2, 1, 1/2. So we can find our common difference by taking our second term and subtracting our first one. So that's 4 over 2 minus 5 over 2, which is negative 1/2. So that's our common difference. So D equals negative 1 over 2. And we need to know our first term. So our A1, our first term, is 5 over 2. So to write it down in our recursive formula, we say A sub n equals A sub n minus 1 minus 1/2. So if we want to know any term, we can take our previous term and subtract 1/2 from it. So we can do a practice problem right here. So we'll find our difference. We take negative 3.5 minus negative 5, which is negative 3.5 plus 5, which equals 1.5. So our difference is 1.5, and our first term is negative 5. So A sub n equals A sub n minus 1 plus 1.5, where A sub 1 equals negative 5. In this second example, we'll find our difference, 1/3 minus 2/15. We need a common denominator, which will be 15, so we'll have 5/15 minus 2/15 is 3/15, which is also equal to 1 over 5. So our difference is a positive 1 over 5. And our first term, our A sub 1, is 2/15. So A sub n equals A sub n minus 1 plus 1/5, where A sub 1 equals 2/15. The next formula is the explicit formula, where you can find any term by taking your first term plus your difference times whatever term number it is. So like if we're looking for our 10th term, we'd put 10 in for n, and then minus 1. So here in this example, our difference, it's pretty obvious that it's plus 2. And our first term is 0. So we'd say A sub n equals A sub 1, which is 0, plus our difference, which is 2, times n minus 1. So A sub n equals 2 times n minus 1, which you can then distribute and get A sub n equals 2n minus 2. So this is terms 1, 2, 3, 4, 5. If we wanted to find the fifth term, we could say A sub 5 equals 2 times 5 minus 2, which is 10 minus 2, which equals 8. And if we look back at our sequence, then we can see that the fifth term is indeed 8. So we'll practice writing the explicit formula. We can find our difference, our negative 1 minus 3 equals negative 4. So our difference is negative 4, and our first term is 3. So we get a sub n equals a sub 1, so 3, plus our difference, so we're going to do minus 4 n minus 1, which we'll go ahead and distribute. A sub n equals 3 minus 4n plus 4, so a sub n equals negative 4n plus 7. So here for our second example, we'll find our difference. 5 over 11 minus 3 over 11 equals 2 over 11. So our difference equals 2 over 11. And our first term is 3 over 11. So we get a sub n equals 3 over 11 plus 2 over 11 times n minus 1. We'll distribute the 2 over 11 into the parentheses. A sub n equals 3 over 11 plus 2 over 11 n minus 2 over 11. So we have a sub n equals 2 over 11n plus 1 over 11. We can go ahead and test this one out. Let's use our fourth term. A sub 4 equals 2 over 11 times 4 plus 1 over 11. So you get 8 over 11 plus 1 over 11 equals 9 over 11. And if we look up here, our fourth term is 9 over 11. So our equation is correct. Next we have summation notation, where we can find the sum of an arithmetic sequence. So for summation notation, we need to know the number of terms, our first term, and our last term. So here we have 0, 5, 10, and then some missing terms, and the last term is 25. So our a sub n is 25, our a sub 1 is 0, but we don't know the number of terms. It would be pretty easy here to say, okay, it's going to be 15 and 20. But in other sequences, they can be much longer, and it's difficult to figure that out. So we'll start here by finding out our explicit equation. So our difference is a positive 5, and our first term is 0. A sub n equals 0 plus 5 times n minus 1. So a sub n equals 5n minus 5. So if we want to know what number term 25 is, we can plug in 25 for a sub n and solve for n. So we'll add 5 to both sides and get 30 equals 5n. Then divide by 5 and get that n equals 6. So we have 6 terms. So now we have the variables that we need, and we can plug that in. So we have s sub n equals n, which is 6, times a sub 1, 0, plus a sub n, 25, over 2. So we get s sub n equals 6 times 25 over 2, which you can simplify that to 3 and 1. So your sum of your series is 75. So right here we have our summation notation. So we're finding the sum from the second term, from n equals 2, to the 20th term. So we'll start out by figuring out what the second term is. So n minus 8, where n is 2, so we'll have 2 minus 8, which equals negative 6. And then our 20th term is going to be n minus 8, where n is 20. So 20 minus 8, which is 12. So now we have a sub 1 and a sub n, but we don't know the number of terms. So to find the number of terms, we'll take 20 minus 2, which equals 18. But since we're including the 2 and the 20, we're going to add one more to that. So we have 19 terms. So our S sub n equals 19 times the first term, which is going to be negative 6, plus the last term, which is 12, over 2. So that's going to equal 19 times 6 over 2, which is 19 times 3, which equals 57. So that's our sum of this series. Next, we want to find the sum of the first 12 terms of this sequence. So we need to figure out what the 12th term is. So we'll find that using our explicit formula. So first we'll calculate our difference, our 5/11 minus 3/11, which is 2/11, and our first term, which was 3/11. So that's A1, this is D. So we have A sub n equals 3/11 plus 2/11 times n minus 1. And we want to find the 12th term, so we'll plug in 12 for n. So we have 3 over 11 plus 2 over 11 times 12 minus 1. 3 over 11 plus 2 over 11 times 11, which is 3 over 11 plus 22 over 11, which equals 25 over 11. So that's going to be our 12th term. So A sub 12 equals 25 over 11. So to find the sum, S sub n, we have the number of terms, which is 12, times the first term, 3 over 11, plus the 12th term, 25 over 11, all over 2. So this equals 12 times 28 over 11 over 2. We'll simplify this 12 and the 2 to get a 6. So we have 6 times 28 over 11, and 6 times 28 is going to equal 168 over 11. So this would be your sum. Next, we have a little bit more of a challenging problem. If A3 equals 151 and A6 equals 139, what's the sum of the first 10 terms in the sequence? So we don't have our A sub 1 or our A sub n, but we do know that our number of terms is going to be 10. So to figure out our A sub 1 and our common difference, we're going to start by writing two equations with the explicit formula. So we have A sub n equals A sub 1 plus D times n minus 1. So for A sub 3, we know it equals 151 equals A sub 1 plus D times 3 minus 1. So we have 151 equals A sub 1 plus 2D. So we have one equation here with two unknowns, so we need a second equation to be able to solve. So we'll create a second equation with A sub 6. So we know A sub 6 is 139. So 139 equals A sub 1 plus D times 6 minus 1. So 139 equals A sub 1 plus 5D. We'll start by solving both equations for A sub 1. So A sub 1 equals 151 minus 2D, and A sub 1 equals 139 minus 5D. Since we've solved them both for A sub 1, we can set them equal to each other. 151 minus 2D equals 139 minus 5D. We'll add 5D to both sides, so we get 151 plus 3D equals 139. And then we'll subtract 151 from both sides. So we get 3D equals negative 12. When we divide by 3, we get D equals negative 4. So we have a common difference of negative 4, which then we can plug back in to one of the equations to figure out what A sub 1 is. So we have A sub 1 equals 151 minus 2 times our difference, which is negative 4. So A sub 1 equals 151 plus 8. So A sub 1 is 159. So we figured out A sub 1. Now we need to figure out A sub n, so our 10th term. So we'll go back to our explicit formula, and we'll plug in A1 and D. So we have A sub n equals A sub 1, so 159 minus 4, because D is negative 4, times n minus 1. And we'll plug in 10. So A sub 10 equals 159 minus 4 times 10 minus 1. So that's 159 minus 4 times 9, which is 159 minus 36, which equals 123. So A sub n is 123. Finally, we can figure out our sum by plugging in S sub n equals n, so 10 times A sub 1, 159, plus A sub n, 123, over 2. So it's 10 times 159 plus 123, which is 282, over 2. We can simplify these to 5 and 1. So we get 5 times 282, which is going to be 1410. So that is our sum of the first 10 terms of this sequence. Finally, we'll learn how to find the sum of an infinite series. It's pretty straightforward with arithmetic series. So your sum of an infinite number of terms in an arithmetic series is going to be infinity if your difference is greater than 0, because your number will just keep growing. And it's going to be negative infinity if your difference is less than 0, because the number will just keep getting more and more negative. So here in this example, we have the sum from n equals 1 to infinity of x minus 4. So our common difference is negative 4, and since that's less than 0, our sum to infinity is going to be negative infinity. In this series, our common difference is a positive 5. Since that is greater than 0, our sum of the infinite series is going to be infinity. In this sequence, you can see the difference is going to be 8 over 11 minus 1, which is 8 over 11 minus 11 over 11, which is negative 3 over 11, which is less than 0. So our sum of infinite number of this series is going to be negative infinity. So you don't even need to necessarily know what the difference is. You just need to know that it's getting smaller. So it's going to be a negative infinity. One application of arithmetic sequences and series is simple interest. So here's a word problem about simple interest. Brooke invests $5,000 into an account that pays simple interest of 5% per year. Write the recursive and explicit equations showing how much money Brooke has at the start of each year. How much money will Brooke have in her account at the start of year 5? So we need to start out by figuring out what our A1 is and what our difference is. So the first year, Brooke invests $5,000. So that's going to be our A1, our initial amount. And then each year, the account pays simple interest of 5%. So 5,000 times 5%. So when we change our 5% to a decimal, we get 0.05. So that's going to equal $250 that's added to her account each year. So our difference is going to be a positive 250. Our recursive equation is then an equals an minus 1 plus our difference, so plus 250, where a1 equals 5,000. So that's our recursive one. For explicit, we have an equals a1, 5,000, plus our difference, 250, times n minus 1, which we'll distribute. So we get an equals 5,000 plus 250n minus 250. So our explicit equation is an equals 4,750 plus 250n. So to find out how much money Brooke will have in her account at the start of year 5, we'll plug in 5 for n. So we have a5 equals 4,750 plus 250 times 5. So a5 equals 4,750 plus 1,250. So A5 equals 6,000. So she'll have $6,000 in her account at the start of the 5th year. And the reason we plug it into our explicit equation is because we can plug in any number here, versus in our recursive equation, we would have to know A4 in order to figure out A5. So in summary, here are our important equations for arithmetic sequences. We have our recursive formula, explicit formula, summation formula, and the sum to infinity. And then these are all of the variables. All of these will be really important in solving arithmetic sequences and series. And that's all. Thanks for watching.